Okay, let's do another problem. Two loudspeakers are separated by a distance of 6 meters. A listener sits directly in front of one speaker at a distance of 8 meters, so that the two speakers and the listener form a right triangle. Find the lowest frequencies for which the path difference from the two speakers to the listener will be an odd 1/2 multiple of the wavelength. Well, if the path difference is an odd multiple of 1/2 of the wavelength, then the two waves will be arriving out of phase. There will be no sound at that point. Alright, what are the given situations? This is the given situation. Two loudspeakers, these are the two loudspeakers, and here is the listener listening the two sounds coming from the speakers. Now the listener is 8 meters from one speaker, that is, this is 8 meters, and the two speakers are 6 meters apart. That means the distance of the listener from the second speaker is this. That is the hypotenuse of this right triangle. If this distance is 6, this is 8, then that hypotenuse is 10 meters. Alright, so once you figure out the diagram, we can now start the problem. What is the path difference between the waves from speaker 1 and speaker 2 reaching the listener? The path difference will be 10 meters. The waves from speaker 2 will travel 10 meters. The waves from speaker 1 will travel 8 meters. The path difference is 2 meters. Alright? When the path difference is an odd multiple of lambda by 2. Now, we are told that we need to find the condition. What are we supposed to find? Find the lowest frequencies for which the path difference, this path difference, which is 2 meters, will be an odd multiple of half a wavelength. Now, how do you write odd multiple of half a wavelength? 2n plus 1 times lambda by 2. This is how you represent the odd integer multiple of half a wavelength. And the path difference, that is 2 meters, must be equal to an odd multiple of half a wavelength. So we have the equation 2n plus 1 times lambda by 2 must be equal to the path difference 2. And we need to find the lowest frequencies. That means the lowest frequencies will correspond to the lowest values of n. What are the lowest values of n? Integer values. N equal to 0 and 1 are the two lowest values. Alright? Two lowest frequencies correspond to n equal to 0 and n equal to 1. So what we will do is, we will assign n equal to 0 here and find the corresponding value of the wavelength. Once you know the wavelength, we can then figure out the frequency. You see that? So, when n equal to 0, what do you have? 2n will be 0, 2n plus 1 will be 1. The left hand side will be simply lambda by 2. Lambda by 2 will be equal to 2, or lambda will be equal to 4 meters. So the lowest frequency that will arrive at that point, completely out of phase, will have a wavelength of 4 meters. Now, if the wavelength is 4 meters, what's the frequency? Frequency equal to V over lambda. V is 340 meters per second, divided by lambda is 4 meters. That is 85 Hertz. That is the lowest frequency that will arrive completely out of phase. What is the next higher frequency that will be out of phase? That will correspond to n equal to 1. When n equal to 1, 2n plus 1 will be 3. 3 lambda by 2 equal to 4. 3 lambda by 2 equal to 2, or 3 lambda equal to 4, lambda equal to 4 over 3 meter. If lambda is 4 over 3 meter, what is the frequency? Frequency is 340, that is the velocity, divided by the wavelength is 4 over 3 meter. What is that equal to? That will be 255 Hertz. So these are the two lowest frequencies for which the path difference will be an odd multiple of half a wavelength. I hope you understood the way I argued this problem out. Okay. Next part of the same problem. Why can these frequencies be heard even if the speakers are driven by the same amplifier? You see, in practice, you still be able to hear these frequencies, although these frequencies arrive at the listener completely out of phase. But the reason why you can hear them is that the sound you hear are not only the direct sound from the speakers, but also the reflected sound from the walls and the ceilings, and that's why you can still hear it. The waves coming towards the listener directly from the speakers undergo destructive interference at these frequencies, but they also get reflected from various parts of the room and reach the listener, enabling the listener to listen to the frequencies.